We're going to look at color now. And so first, we're going to look at color in terms of how we discovered it. So color is in the eye of the beholder, and we're going to talk about that more in terms of how we perceive color on another screen. So Isaac Newton was the first to discover that light is composed of different colors. And the way he discovered this is he discovered that a prism could separate white light into a certain arrangement of colors. So just like over here. So you have a prism, triangle-shaped prism, and as the white light goes in, it is broken into all of the different colors of the rainbow. So red, orange, yellow, green, blue, indigo, and violet, which are your answers right here. So red, orange, yellow, green, blue, indigo, and violet. And, each color has its own wavelength and frequency. So that's in the one about the spectrum. It talks about the different wavelengths and frequencies of the colors. However, each color is still going the same speed, just like with sound. It doesn't matter what the wavelength and frequency is. All it matters is what kind of wave it is and what medium it's in. That determines its speed. So since all of these are still going through air or going through our material of the prism, they will have the same speed here, they'll have the same speed here. What happens to create this rainbow effect with a prism is that red light has the lowest frequency, so it has the longest wavelength. So it does not bend as much because as being a longer wave, it's not affected by all these particles as much. Whereas down here, since the wave is really, really tight, the particles inside the prism affect it a lot more, bending it more. This is why sunsets are red, is because only the red light is able to get through all of the air from where we are all the way to the horizon. The blues and greens and indigos and all are unable to get through, and so only red and orange is. Hence, sunsets are red and orange. Red light has the lowest frequency, therefore it carries the lowest energy. So frequency and energy are directly related. Violet has the highest frequency, therefore it carries the highest amount of energy. So the highest energy. So if you remember from chemistry class, you did a flame test, and do you remember which one is hotter? That would be blue. And now you know why. Blue flames are hotter because blue light has higher energy than red light does. It's all about the frequency. Blue light has a higher frequency, red light has a lower frequency, so they have different amounts of energy. So what is color? We perceive color by the frequency of the light. So we don't look at orange or we don't look at red. We're looking at certain frequencies of those light waves, and then we interpret those as red or as orange or as blue. We have cones in the retina, so you have rods and cones. Rods deal with perception, it's just grayscale, and then cones give you color. So in your eye you have three sets of cones. You have blue cones, green cones, and red cones. And depending on how well these cones work determines how you perceive color. And this is where the whole colors in the eye of the beholder. It's based on how your eye interprets that information. Whenever someone is colorblind, it means they're missing a set of these cones. So if a person is green colorblind, they're missing the green cones, so they're only able to perceive blue and red, and vice versa on the others. We'll talk about why blue, green, and red are the three colors of the cones in your eye. So now we're going to look at color rules. The color of an opaque object depends on what it reflects. So the reason why a shirt looks red is because it reflects red. If all colors are reflected and none are absorbed, we see white. This is because if all the light is reflected, all the light together forms white light. If no colors are reflected and all are absorbed, so it's either reflected or absorbed, if all are absorbed, we see black. So black is the absence of light. So why is it a bad idea to wear a black shirt on a hot sunny day? Because black absorbs all of the sunlight. White reflects all the sunlight. That's why whenever it's really hot outside, you try to wear as light of color as possible so that it reflects all of that light. The color of an opaque object also depends on the color of light. For most things, we're going to assume white light, which means it reflects all of the colors potentially. But what if we have a certain color of light, for example, like in a photography room, where you have only red light? If a substance reflects red, it will look red, period, because it will reflect red light. It will also look red in red light, because red light includes red, and so it will look red. But if instead we have a green light, so for some reason we had a green light instead of a red light, red does not reflect green. It absorbs green, and so we'll see black, because the red pigment will absorb green light. This is the other way that color is in the eye of the beholder. It matters what your eyes are, and it matters what light you have. Now let's look at filters. The color of a transparent object depends on the color of light. So let's look at a blue filter. A blue filter will transmit blue light and absorb everything else. So if you shine white light into your blue filter, you'll see blue. If you shine blue light onto your blue filter, you'll see blue. But if you shine a red light on the blue filter, no light will pass through it, and so it will appear opaque and black. So now let's talk about these colors of light. So almost any color can be generated by mixing red, green, and blue light. If you've ever looked at your television, so if you have an older style television, you'll notice that you can adjust red, green, and blue, but nothing else. If you have an HD TV and you have, your component cable, there's always a red, a green, and a blue connector along with your audio. The reason why is because red, green, and blue are the primary colors of light. So primary colors of light. And that's because if we take red, green, and blue together, we will get white light. When you combine colors of light by adding them together, it becomes brighter. So light becomes brighter as you combine them. Therefore, mixing light is an additive process, which means you add them together to form a brighter color. I have a great demo for this. If you combine green and blue together, you get kind of a lighter green-blue color, which we call cyan. So if you know a cyan crayon, you know it's a light green-blue color. If you combine red and blue together, so red and blue make kind of like a purplish color, but we need a lighter version, which would be magenta. Magenta. There we go. So if you combine red and green together, this one's really interesting. You don't get brown, you get yellow. So you get yellow light. And then, of course, if you combine any of these together, again, you get white light. So this is how you can take red, green, and blue in your television and form any color that you see on that television. It's because as you add them together, you get lighter and lighter until you get white light. So now let's talk about pigments. Mixing pigments is the opposite of mixing light. Pigment is paint, basically. It's color that you put on an object to reflect. This is a subtractive process, which means we're going to subtract colors out. The more colors you mix, the more is absorbed, and so the less you see. Yellow, cyan, and magenta are called the three primary pigments. And notice that these are the three colors that we created in light. See, cyan, magenta, and yellow. Yellow, cyan, and magenta are the primary pigments. If you've ever looked at a color cartridge on your printer, you will notice that you always see these three colors, this yellow, this light greenish blue, and then this very bright hot pink color. So a cyan pigment will reflect green and blue because that's how we form it. Therefore, it must absorb the other color of light, which is red. A yellow pigment will reflect red and green because that's how we get yellow. Therefore, it must absorb blue. And then magenta is red and blue, therefore it must absorb green. So, how do we use primary pigments to produce a blue color? Well, we don't have blue paint. We form blue paint using yellow, cyan, and magenta. You shine white light. White light contains red, green, and blue, our three primary pigments. A cyan pigment will absorb red, and it reflects green and blue. A magenta pigment will absorb green and will reflect blue and red. Here's where the subtractive process comes in. The only color that these two have in common is blue. This one absorbs red. This one absorbs green. So the green and the red go away, and all that's left is blue. So to get a blue color, you mix cyan and magenta. Now the question is, how would you get white on a piece of paper then? If you keep adding these pigments on, it gets darker and darker. The way you get white is you leave it blank. So if you put a white sheet of paper in your printer and there's a spot that's white, it'll be blank. There won't be any ink there. If you put a yellow sheet of paper in there, anywhere white on the print will actually appear yellow because there's no ink there. And so whatever color the paper is the color you'll see in the location of white. So an easier way to figure this out is to do like a chart. So white light is a mixture of red, green, and blue, and we're mixing magenta and yellow. So magenta is formed by reflecting red and blue light. So what we're going to do is mark these with an X. Yellow is created by reflecting red and green light. So the way we know what color will appear is we have to figure out which one they both have in common. The only one they have in common is red. So if we mix magenta and yellow pigment, we'll get red. If this was green light, it would appear black. If it was blue light, it would appear black. If it was red light, it would appear red. So white light and red light, these two pigments will create red.